Okay, okay, I think this one we done already in our last class. Okay, let me check. And so talk about the applications of this three-phase AC controller. So it's basically, used in industry, what we call soft starter. Okay, so yeah, basically they are using the same thing. Of course, the difference is the controller, all right, how efficient or how effective, okay, the controller, okay, they use. Let me just check one thing here, because I remember I do upload this one in files exchange. I'm not sure is it still there or I have removed it long time ago. Oh, okay. I do have it. Okay, for this one, right? Okay, I'm using this what we call the SimScape, all right? The specialized power, right? To do it. Yeah. Okay, you can find one of my this very old one which I did. I think 2016. All right. So it's three-phase AC voltage controller model. Okay. The difference is that I have actually created a blocks here, okay, which represent the 6 of this or the 3 set of these thyristor, and then I'm using, back then I think we don't have all these SimScapes model yet, okay, this one. So I was using the specialized power system, okay, to do the control. You should be able to get the same result. And of course, you will notice the block I use is a little bit different because again, okay, that was how many years back? That was 7 years, right? 4, 5, 6, 6 years. Okay, that was 6 years back. Okay, MATLAB still do not have this what we call this thyristor 6-pulse generator. So you can, in case you all have difficulties of making this work, you can always download this one, okay, from file exchange. All right. So it is called three-phase AC voltage controller model. Okay. Okay. So this. Okay. So yeah, hopefully you all can download and have a look. Okay, on it. Okay, so yeah, it should produce the same output lah, all right, as this one. Okay, so after that, okay, after this one, now we have to move on to the next type of AC/AC controller. Okay, that is what we call cycloconverter. Okay, cycloconverter here. Now, the previous one, okay, is basically we are trying to control the AC voltage magnitude, right, or the power magnitude by, chopping off the voltage waveform so that, it will actually change the area under the curve. It will reduce the area under the curve so that you will have a lower voltage, but the frequency remain. Okay, so now the second part is that cycloconverter basically allows you to control the frequencies. Okay, control the frequency as well as the magnitude. So now, of course, nowadays, not say nowadays, even in the old days, okay, cycloconverter are usually used in a very large machine. Okay, it's not applicable in a very small machine. Okay, large or small is in the sense of, like you can see, the major application, right? Okay, is to actually control the AC motor. Okay, up to 50 megawatt. Okay, if you are talking about 1 kilowatt of motor, which is roughly 1.5 kilowatt is roughly 1 horsepower lah. So this is megawatt. Okay, this is megawatt. So you won't see many of this in the market because it's designed for large applications. Okay, and then it controls the frequencies usually between 0 to 20 hertz. As we know that our frequency is, is 50 hertz or 60 hertz. So in fact, this is a pretty much, high speed, because if you multiply by this 60, right? 60 multiplied by 60, you actually get 3,600, okay, RPM. So that is actually a very, very high speed. Okay, so most of the large motor, okay, they don't, industrial motor lah, let's say, they don't really operate at that kind of speed. Okay, so like for example, conveyor, you do not need, this 3,600 RPM. Even our car, right, normal lah, roughly we are, when you start your car at ideal mode, right, it should be 1,000 RPM, right? Only the moment you press your accelerator pedal, then it will go up to 3,000 or 4,000. Okay, the moment you engage your gear and start driving, right? So you will notice your RPM is actually in between 2,000 to 3,000. That is good enough for normal driving. Okay, of course, we are not talking about speeding on highway lah. You can go up to 4,000 or 5,000. I don't think so. Under normal driving condition, you're going to do that. Okay, so what I'm trying to stress here is that in 50 hertz or 60 hertz, if you connect it to direct online, okay, to the power, so eventually it will rotate at this speed. So this is considered a very, very high speed. All right. So the cycloconverter is basically to reduce the frequency, not increasing the frequency. Yeah. Okay. I need to stress this, even though it was designed to so-called chain, but back then in the old days, okay, it was designed to reduce the frequencies, so that even the like say a car, right? You won't immediately the moment you start the engine is already running at 3,600 RPM. Okay. So it's designed to actually reduce the frequency. But of course, if you have any application, okay, that you require to increase the frequency, then you need to use the DC, the AC drive, which is made up of the DC to AC converter, which I show you all in the previous chapters. Okay, that like I said, our modern EV electrical vehicle, right? They don't use cycloconverter. Instead, they use the AC drive, okay, which is the DC to AC converter, which can control, increase and decrease the frequencies. Okay. All right. So how this cycloconverter works? Okay. Now cycloconverter works, okay, with two sets of what we call the full bridge rectifier. Okay, you can see this is one set of it. Okay, so this is one set of full bridge rectifier. Okay, and this is another set of full bridge rectifier. The difference between these two sets is that one rectified positive, so that's why it is called positive converter. Okay, the one that rectified the positive will be called the positive converter. The one that rectified, okay, the negative, which is the negative converter. Now both, right, are actually connected to the same AC line. Okay. Another thing I need to stress on, nowadays cycloconverter are usually three-phase. Okay. I no longer see any single-phase cycloconverter anymore, okay, in our current industry applications. But still, you need to understand a single phase in the sense that in order to understand the basic operation principle. So when you see that, okay, this is the VS, right, the sine wave. Okay, now if we rectify, okay, the positive side, right, you can see the first part of this, the first positive cycle, okay, and the next one, the negative cycle, right, after rectified, it will turn to the positive cycle again. Okay, like that. So it is actually make use of this positive cycle. So the plus minus is here. So it always give you the positive. Okay. And the moment it comes to the second cycle, okay, this one is turned off. Okay, and this one is turned on. All right. So when you turn this on, it will give a negative cycle. Okay, so this will have a plus here, minus here. Okay, so this is the load. So you will get the negative cycle. Okay, so and then the process repeat itself. So by doing that, right, you are actually reducing the frequency to half. Okay, if this is 60 Hertz, by doing that, right, you will notice that this will become the positive cycle, right? And this will become the negative cycle. And similarly, this one will become positive cycle, right? And this become negative cycle, and this become positive. So it will give you 30 Hertz. And similarly, okay, when you choose to use a positive cycle for, two cycle here, so this part will become positive, and this part will become the negative cycle. Oops, sorry. Okay, so remember the AC motor rotate based on the alternating, voltage and current, right? So you have a positive all the time positive. Okay, and then this one you will have divided by 4, right? So you will have 60 divided by 4, how much? Anyone can tell? 60 Hertz divided by 4. Okay, you will have 15. Okay, you will have a 15 Hertz. So it's the same principle apply to 50 Hz system. Okay, the same principle apply to 50 Hz system. Okay, now this is the basic principle how you reduce the frequency. And there is a catch here in the sense that, right, how about if I want to do like, 40 Hz in between? You can, okay, but it won't be very stable because you just need to turn on this a while, a half. So it's a division between 2, 4, or 0.5. Okay, if you take these 1, 2, 3, so it's going to be 1.5 or divide 1.5. Okay, so that means you have limited control. 1.5 means that, okay, let's say you change this 1.5 cycle lah, okay, into a positive cycle, and the other 1.5 into a negative cycle. Okay, something like that. Then you can have 60 Hz or 50 Hz, okay, that is divided. Okay, that is divided by 1.5, okay, which is 40 Hz. Okay. So it has some limitation in the sense that you cannot like reduce 1 Hz, 1 Hz, 1 Hz, right? So, but you want to do that, like I said, you need to use a more advanced DC-AC converter AC drive, okay? So that can be used to control at more precise frequency that leads to a more control to a precise RPM, okay? So up to this point, any questions? Because you need to understand this in order to understand the rest. Okay, so it's basically two set of AC-DC converter. It connect in the opposite direction. Of course, you do not turn on both at the same time. If you turn on both at the same time, it causes short circuit. Okay, it causes short circuit to the incoming AC, and of course, yeah, you're going to damage these two set of rectifier. Okay. Okay, now how about now we know that this is the way that we control the frequencies, reducing the frequency. Remember, cycloconverter reduce, it will never use to, I mean, it won't be able to increase the frequency. Okay, so you have to be very careful on the application that you use. Okay, now how about controlling the power? Okay, now controlling power is the same as, the firing angle to turn on and off is 0, right? You firing angle at 0 is turn on, right? But you increase the firing angle, what happens is that, okay, again, let's say, you increase the firing angle, then you will start to chop it off, right? So again, you can see that this is 1/3 of the frequency, which is divided by 3, okay? 1/3 of the frequency. You divided by 3, then now you no longer get full wave here. Okay, it has been chopped off. So by using these equations, I believe you all can recognize this equation, right? This is a single phase equations. Okay, single phase AC controller equation where your alpha is your firing angle. Okay, then you can actually control the magnitude, the power, as well as the frequency. So for any motor, right, the frequency determine the rotational speed, RPM, and the power determine the torque, okay, of the motor. Full power, you get the full torque, okay, of the power, and you reduce the power, you actually reducing the torque. You can control the torque in another way, okay, of a motor by controlling the firing angle. So this part is pretty straightforward. Okay, it is a single phase, it's applicable, okay, to this cycloconverter. Okay, so I have made one of these example in my lab. Okay, you can download it from here. Okay, I don't expect you guys to what we call to do it. Okay, so yeah. You can download this one, all right, and then you can actually run it. Okay, let me see. Cycloconverter. Okay, I'm opening my, wow, this is a different version I have. Okay. Okay, something like that. Okay, the one I show you now is I make a bit of modification here that so that I can control the wattage, okay, the torque, okay, but this one only control the frequency, it does not control the torque, okay, but it should show the same result, okay, when you run this. Okay, this one, if I'm mistaken, I'm following, yeah, the textbook, okay, which is the American wattage of 60 Hertz. And you look at the frequencies. Okay, so it's going to be, yeah, all right, you can see that is 1/3 of the frequency. Okay, so it is the 1/3 of the frequencies. And then we look at the FFT. Obviously, like I said, when the waveform is distorted, right, the THD is going to be very high. Wait, now it show on the other side of my monitor. Every time I have this problem. Alternate control, okay. Alternate space. Okay. So, all right, let's see. Okay, frequency, okay. We need to see, this is only one cycle. I think we need to see, it's not 10. How many cycles? It's 12 cycles. Okay, let's see all the 12 cycles. Everything is nice, then we will look at. Okay, all right. So you will notice that, of course, you can, if you don't want to see this, you can put a THD block here. So immediately you can see the THD, okay, will be over 136, okay, 136, what we call this THD, okay. And you will notice that now the fundamental, right? Fundamental supposing to be 60 Hertz, but you can see the highest peak is actually at this point, which is around, I don't know, the scale here, it's on over 3, right? So it's 20 Hertz, yeah. So the scale here is 20, okay, 40, and this one is 60, okay. So you can see that the highest is even though the fundamental is 60 Hertz, okay, because we know the fundamental is 60, okay, and then the actual have the highest magnitude or the frequency, okay, is actually 20 Hertz, unless we change this to 20. Let's see. Oh, cannot. So we have to still fix on this. So this FFT thing, you have to be very careful lah, okay, to actually see, oh, it is, you know, the one with the highest peak, okay. Let's see. I think this one should be already the higher of the, say 100%, right? Is this one, which is the fundamental, but it's higher than 100%. Okay, it's 100%. Yeah, it's actually even more higher. I don't know how high is it. This one, I think we cannot show the highest point. Okay, so it will have a very high THD, and then and of course, you know, it will cause heating, okay, to the motor you are using. That's why cooling the motor become an, you know, essential part already, lor. So usually they are using water cooling to cool the motor. Okay, the heat actually come from here, but again, that the heat generated by this cycloconverter waveform is not as high as those with the, what we call, with the, you see, if you look carefully on the harmonic here, this is just extra information for you guys. Nothing to do with this course, just for your information. Okay, this is first order, right? 100%. Okay, and we got second order, we got third order, we got fourth order, right? Now you will notice that, okay, the usually the problem with harmonic is third order and above. Okay, very rare we have, even the second order is almost zero. So all the harmonic here, okay, is considered low order harmonic, or sometimes they call it, because you see the operating frequency, right, is 20 Hertz. So it's considered subharmonic, meaning that the fundamental is 60, your harmonic is lower than the fundamental, we call subharmonic. So subharmonic does not really produce that much heat as compared to the high order harmonic, those third harmonic, fifth harmonic, 7, 8, and so forth. All these harmonic, even the magnitude are very, very low, even like 3%, 4%, it will actually generate a very high heat rather than those, you know, harmonic with a high percentage here. Okay, you can refer these to the standards. The standard will tell you, okay, especially the IEC standard and the IEEE standard, it will tell you, oh, this harmonic, right, you shouldn't go above how many percent. Okay, it will cause problem. Okay, so hopefully this will explain the dilemma, you know, why harmonic so high, people still use this cycloconverter for real application. Okay, because it's a subharmonic. This is lesser than the second harmonic, okay, third and second. And then of course, it's just like the transistor we are using, right? When we are using a transistor operating a very high current, right, we know that it's going to heat up. Okay, then what you need to do, design the heat, you need to design a proper heat sink, right, just to help dissipate, because nothing else you can do already, the heat is there. Okay, and we know that the heat, you know, sometimes can go up to 100 degrees Celsius, which is high enough to boil water. Okay, but if you operate the same transistor at very low current, then you don't even need to put a single heat sink. As simple as that, lah. It's just like our car engine. We have a, you know, car engine. We have this radiator water cooling, right? Otherwise, right, it won't be, you know, what we call this cool. I mean, it will be overheat, for sure, if we have our, what we call this radiator and cooling system have issue, lah. Okay. All right. So if you want to control the magnitude, okay, now the magnitude is 120, right? Because the AC here, the peak is 170, so RMS is 120. Okay, correct. And these are the waveform. Okay, we have. Now, if we want to control the magnitude, like I said, I just need to set the firing angle. I just need to reduce the time 0. So I set the firing angle is pi over 3. You can see now the voltage reduced to 107. And we look at the voltage, you can see now I have chopped off. Okay, now these are AC, just like how we did to a single phase AC controller. So with this combination of controlling the voltage and controlling the, what we call this frequencies, okay, we can control both. All right. So you all can download this one. I put in my lab. Okay. Okay, the one I put only control frequency. You cannot control the magnitude one because I just want to simplify this part to make it yeah, look simple in other words. Okay. All right. Okay, so these are some of the setting. Okay, of using this method. I mean, you can download it anyway. Okay. Then you divide the frequencies. Okay, this one is 4, right? Divided by 4. And similar again, you can use the FFT. Okay, and you can see the total harmonic. I'm not sure is this something wrong with this calculation or what. It's a bit scary lah, 91,000%. Okay, I mean in real life, I never see this high lah, THD. Okay, but anyway, okay, you can actually try to put the THD block lah to actually see whether it is correct or not. Okay, we have this THD block, right? Where you can connect and it will show you the THD. Okay. All right. Okay, and then same like I said. Okay, it's a sub order harmonic. Okay, those higher order will usually have a very low magnitude. Okay, still okay, it will generate heat on it. Okay, so for the single phase, any questions? Hello? Oh, okay. Wait, just maybe let me try the THD block on this one and see. So we have the THD block here. Okay, very rare you're going to do the FFT, unless it's a research project. You only need to look into that detail. Okay, most of the time we only look at we will use this block to see lah. Okay, where is I think it's under measurement. Under measurement, where is it? THD. Okay. Okay, THD. Okay, here. Okay. 60 Hertz. Okay, nothing much to change. Okay. Wow, 1,000 something. Wow, it's quite high, huh? Yeah. 1,000. THD, yeah. Not sure this one is percentage or not percentage. Anyway, it will show a very high THD. Okay. And I think there is another THD block here. There are 2 in this electrical system. I'm not sure which one is it. Utilities, no. Breaker, no. Yeah, see there is another one here. This one will give you straight away percentage. And of course, THD measurement, right? If I'm not mistaken, this one is measure just one cycle. So it will give you different THD. Because you measure 2 cycle, 3 cycle, it will give you roughly a bit difference. And also remember this one because I also used to control the voltage, right? Because I already chopped off the thing. So you can see it go up 10 times, okay, of the THD. Wait, how come this one gives 0? I think I need to change it to, yeah, both block operate differently. Yeah, what, same, 1398, okay. So it's 1398, okay, of this THD. Okay, this one is already in percentage. This one you need to multiply another 20 in. Okay, so just to make sure that yeah, you know how to use it. Okay, the FFT should show you this one as well because this one, like I said, we eventually already chop off them. Okay, we already chop off them. So we will increase the THD. So THD is actually much more on the power system issue. Okay. Okay. So come back here. Okay, now to single phase to three phase to single phase. Okay, how about if your input is 3 phase and you want to change to single phase? Okay, again, you just need to have a positive. This what we call this. This is negative. This is positive, and this is positive. This is negative. Okay, so you connect your 3 phase. Okay, to this what we call the positive cycle. This is a negative converter, this is a positive, and to the load. Okay, so you need to control in a way that how many cycles you want it to be on the positive side and how many to the negative side. Okay, so same principle. Okay, instead of the drawing is actually the same. You look at it, they actually put it together. The single phase one, they put it on both sides. In fact, if you put this set over here also can. Okay, if you ask me, I prefer this drawing. Okay, because you remove these 2 transistors, it becomes single phase to single phase. And you add another set of this, it becomes 3 phase to single phase converter. Okay, so this one I didn't do any what we call this examples. Okay, and of course, like I said, usually we don't do that as a standalone. So in practical, this is what happened to a 3-phase cycloconverter. Okay, again, you will see that this is the motor. Okay, a 3-phase machine, and 1 phase here. Okay, you will have a 3-phase. Okay, positive converter, negative converter, right? All right, it will connect to 1 phase of the coin. Okay, of the stator lah. In other words, you connect to 1 phase of it, and then the second phase still the same set connected to the second phase stator, and the third phase connected to the third phase. Okay, and of course the complicated part is the controller part lah. All right, the controller part is the complicated part, and you will require how many thyristor? Okay, we got 6 here, we got 12 here. All together, we need to have a 36 thyristor. Okay, to construct this three-phase cycloconverter. But the higher the phase you go, right, the lower the harmonic it is lah. Okay. Okay, example. You look at this. Okay, the light color one is the three-phase. Okay, and the one in the bold line, okay, is the output, right? That's mean here, okay, because it's taking in three-phase one, so the output is here. So it's more sinusoidal here, right? It's more, I mean the outline lah, only the outline lah. Okay, it does have high harmonic. It's not as high as the one we showed just now. Okay, and of course with the proper firing angle control, right, you can actually, you know, control the frequency. Okay, this one you can control the frequency, like this one, you know, 1/20 and so forth. So of course, if you have to control three set, okay, with the same frequency, you cannot like putting this one is 20 hertz and this one is 10 hertz. And if you like this one is 50 hertz, you're going to damage the motor, because the motor will be what we call, it will cause what we call a phenomenon called this torque ripple. That means it rotates, right? It does not rotate very smooth. It will, because they have different frequency at different, you know, it will have what we call torque ripple, jiggling, you know. The motor will be like vibrating very, I mean, when you see motor vibration, something is have to be careful already lah. Of course, it can be due to mechanical part as well. The bearing also can cause a problem. And yeah, of course, normally you don't do that lah, right? You will just to make sure that we have to have the same frequency of 20, 20, 20, so that the motor will rotate at, you know, at the speed of 20 hertz. Okay. Okay, I didn't construct simply because MATLAB itself already have this model inside MATLAB. So you can actually, yeah, you can just type 6 files, cycloconverter. You can play around with it lah. Okay, if you type here 6 files, cycloconverter, it should pop up. Okay, so yeah, it actually pops up here. So you just, yeah, and then open the model. It's going to take some time. Okay. All right. Okay. This one, let me close it. Okay. 6 files. Okay. Cycloconverter, 3-phase. And then where they put the scope? Okay. Let me just run first. It should run. Okay. Okay, it show one of the half cycle only, because I think it's the time here lah. I'm not sure. Okay, it's highlight, you know, the phase A half positive cycle. Okay, it doesn't show the negative cycle. Let me see. I think there must be some scope here. Okay. Let's see. Got. The scope will show you lah. Okay, the positive cycle, negative cycle, and so forth lah. Okay, by reducing the frequency. Okay, so each of these, when you open, right, is again, like I said now, it's just a 2 rectifier blocks. Okay, it's only a 2 rectifier blocks. the complicated part is the controller. Okay, how you want to, program it to control the thing, then you need to construct it here. Okay, so that will show you how the example you can just, so this one, that's why I don't need to upload this already inside MATLAB as examples. Yeah, this output or the scope. Oh, I think there's another scope. Will show all three phases output. Okay, that is connected to the load. You see the load they put is just a resistive load. For example, of course, in the real applications, is usually used to drive a motor. Okay, so now what is the application? Okay, the real application of the cycloconverter, okay, is mostly for the mailing machine and of course for ship. Okay, not small ship lah. We are talking about cruise. Okay, and the cruise ship, right? The big ship will have big motor there. Okay, and then the ship, right, won't be running at a very high RPM. Okay, so they usually use a cycloconverter to reduce the propeller rotation to control, okay, the propulsions of the ship. Okay, and yeah, like I say, they have a lot of cooling inside. Okay, ship is on the water anyway. Okay, and of course, in practice, it looks something like that. Everything is inside a cabinet. Okay, there are big thyristor inside each of them. Okay, so yeah, ABB actually have this product. Okay, like I say, you won't really see it off the shelf because it's something expensive and big. You need to pre-order. Okay, you need to pre-order so that they can go and install. Submarine is one of them lah. Okay, when submarine submerged into the ocean, it is not powered by the diesel. Submarine got two engine. One is the diesel engine where it's surface. Yeah, it uses diesel engine. When it's submerged, it switched to electric. Even this one they already use it since World War II. So it's a very old thing already. Since World War II, right? I think the best submarine in the world is the German submarine, the U-boat lah. Okay, so back then they already, even the battery, the motor, everything are very primitive lah, very old. Okay, things. Okay, electronic is still not available that time. Okay, of course, they already use electric motor. Okay, what I need to stress is to use electronic motor. How they control it, I don't know. We don't have much document on this. In the 1940s, okay, transistor not even been invented. So most likely they will use either mercury valve. I don't know. Back then, if there's only electronic valve can do this type of control. But anyway, when it comes to a modern world, they already have this thyristor, so they use it for the what we call cycloconverter. Okay, so this is one of the example. I say, unless you're working in the marine industry, then you may have a chance to have a look lah. So it's like it's considered part of the AC drive. So not all AC drive are DC AC converter. Okay, so like this one is a high power. You can see it can go up to 27 megawatt. You just imagine what kind of application need. Your car, right? Our car is only kilowatt, right? Tesla only use 100 over kilowatt. It's already good enough for car. Okay, so megawatt, of course, it's going to be something huge, like big ship. Then you need a megawatt motor, okay, to actually drive it. Okay, so up to this point, any questions?
No, sir.
Okay, thank you. Okay, so basically we done this cycloconverter already. Okay, not much calculations. There's only one equations. Okay, what you need to do is you just need to remember, the drawing lah. Okay, for example, okay, not the the very basic 3-phase to single phase, okay, or this simple drawing, and of course the waveform lah, okay. Don't worry, I won't ask you to draw this, okay. The most is on draw this lah, okay, because it's just a set, okay, of a motor. Okay, so after that we move on, okay, to another types of AC controller that is applicable in this grid, okay, electric grid. So far, right, our AC controller is applied to like resistive load, the motor load, right, cycloconverter and AC controller, single phase, okay, 3-phase, source starter, right? So now we move on to another application which is called FACS. Okay, FACS stand for Flexible AC Transmission System. Okay, Flexible AC Transmission System. Now, as we know that our transmission line out there, right, in the old days is totally not controllable. Okay, like the high watt. I'm talking about the high voltage transmission line, the 132 kV, 275 kV transmission line. So in the old days, right, it's basically not controllable. Okay, of course, now modern day already, we already have this device to help us to actually control the power flow, okay, between line. All right, and okay, first of all, okay, the purpose of the FLEX is a flexible AC transmission system. So to control transmission line, which is greater than 100 kilowatt, okay, for power flow. Okay, so you can control how much power you want to the line to carry, in other words. So there are a few ways of what we call doing that. Okay, the first one is called SVC. SVC stands for static var compensator. All right, so it's a reactive power, VAR. Okay, var reactive power control. You can control how much real power and reactive power, okay, to actually put on the line. And under SVC, there are two types of controller, TSC and TCR. Okay, what is TSC? TSC is thyristor switch capacitor. Okay, TCR is thyristor controlled reactor. Okay, so both you can see on a transmission line, right? When you add capacitor, it will be in the what we call, it will have a leading current, okay, and then you add a reactor, which is inductor. Okay, in electrical industry we call it reactor. We not call it inductor. Inductor is only for electronic converter, so make sure that you understand that. Okay, they mean the same thing, it's only the size difference. Okay, and this one will give you a lagging current. So with this one, you actually can control how much active and reactive power you want to control by using what we call the SVC. Okay. The other one is called StatCom. Okay, StatCom is static compensator based, which is the IGBT based control of SVC. Now this SVC only controlled by using thyristor. Okay, but if you use IGBT to control it, right? So it's called StatCom. Okay, static compensator. Okay, so both perform the same job. The only difference is the control. Okay, control switching are different. And then another difference is that StatCom currently cannot handle a very high power, what we call this transmission line power control. Okay, only this TSR can deal with a higher power flow control. And the next one is called TCSC. Okay, TCSC is a thyristor control serial capacitor. Okay, so again, you put a capacitor in serial to a transmission line, you control it, you actually can control the power flow. And another one is called UPFC, Unified Power Flow Controller. This is also IGBT based off TCSC. Okay, so for us, we are going to focus on the red color one. Okay, be thyristor base. All right, and of course there are any other different types of compensator lah, SVC lah. These are not very common one. Okay, FCSC. This one I also forgot what is that already. But these are the top. SVC, you can see it in DMB is using it anyway. StatCom usually you at the load side, which is the industrial side. Okay, SVC are usually used at the grid side. Okay, because it can handle higher power. Okay, in megawatt, and then StatCom usually at the grid side. Okay, this one also at the grid side, and UPFC also at the load side. Okay. Okay, so for power flow, you may need to understand a bit of this. Okay, now in our power system, right, it consists of bus. When you all study power system, right, this is what you all study, like IEEE 5-bus system. Okay, and we have IEEE 14-bus system. This is for you to simulate the grid. Okay, a small grid. Okay. Now, every bus, right, represent a substation. Okay, a substation. Okay, you can see this is the generator. It passes through one bus, consider one substation. Bus 2, bus 3, bus 4. Okay, so one substation means that one location. Okay, one location or within the city, and of course they have what we call this line that is connected from one bus to another bus, and this is another substation. You can clearly see that, right? The power is actually come from here. Okay, yeah, it distributes to the load. You can see that the load is here. On top is the load. It can be housing area. It can be the industry area. All right. So you can always see that. Okay, the grid system, right, is an interconnect system. Okay, it's interconnect system, and when one of the line broken, okay, they will still have power. Like for example, if this line broken, okay, this bus still can get the power from bus 2. Okay, it still can get the power from bus 2. And of course, if this line also broken, then of course, this bus no longer have any power. Okay, so again, this is another. This IEEE is actually coming out with many types of this system for you to model the power system. How complicated you want? Like this one is a 14-bus, so it will model a much more complicated grid system. Okay, G is the generator. Okay, from one part to another part. And then if we look at our map, right? Okay, this is our Malaysia rail power system. Okay, so if you look at the map itself, you can see that. Okay, now we can just assume that each of the dot here is considered one bus. Okay, each of the dot can consider one bus. You can see they are code there lah. Okay, TMB using 4-letter code K, T, and N. They have a meaning of it. Like this one, I know YGPE lo. YG is Yongping. Okay, YGP is Yongping. Okay, and then some I don't know, they are long name. But when you look at this type of labeling, it's definitely the TMB naming. And you can see that currently in Malaysia, our highest transmission line, OHL is overhead line, 500 kV. You can see we have a 500 kV somewhere here. Yeah, this is Selangor, right? We have Selangor all the way connect to Perak. Okay, we have this, and then the rest, okay, is 275 kV. Okay, and of course you want to look at more detail, it will be something like that. Okay, each of the dot, okay, is consider one of the buses. Okay, these are the very huge bus lah. Okay, you can see. So yeah, if you look at, you calculate, I think there's going to be more than 100 bus. Okay, yeah, you can simulate that if you want. Okay, of course, you need a very powerful software like Dick Silent ETABS. Okay, that will help you to simulate much more complicated system. Okay, MATLAB, I think 14 bar is almost okay. It depends on how strong is your CPU lah. Okay, so what I'm trying to say is that how this utilities company like TMV controlling the power flow. Okay, how much power I want to deliver here, how much power I want to send over this line. Okay, it's all controlled. Okay, by what we call this fax device. So this entire, from the north to the south. Okay. Okay, now before we go into further on this SVC, okay, you may need to understand this. Okay, you can download this in MATLAB File Exchange, which I have made this. Okay, now imagine there are two bars here, and we have a transmission line. All right, so this transmission line will have a line reactance of 50 ohms, for example. Okay, so you can actually calculate the real power and the reactive power, okay, basing this equation. Okay, the real power, the reactive power. And then on the source side, okay, source 1, source 2, okay, they will have two sources anyway, because all the grid, like I say, is interconnected. Okay, it's interconnected. And you can see that the wattage is 275 here. Okay, if the wattage here is 273, they can be never the same. They will have slight difference. And then the phase angle at this point is 0. And the phase angle, let's say here, is 10 degrees. Okay, you will actually find that the power flow is from the source 1 to source 2, like the arrow show here. Okay, and the real power, of course, on the transmission line, the real power is all in megawatt. You are transmitting 260 megawatt from source 1 to source 2, and you are transmitting 10.8, okay, mega VAR reactive power, okay, from source 1 to source 2. And the wattage difference between the two sources like that. Okay. And obviously this is the leading, the V1, or not the V1, the V2, okay, the V2. So you can see the phase difference. Okay, you can see the phase difference. And then, okay, if my wattage increase, you see, this one is 273. If I put 0, same. What happens is that I can actually cancel the reactive power, only transmit real power, just by adjusting the magnitude of source 2. Okay, equations are the same. And then move on. Now what happened if both sides also same, but the angle just now was -10, right? -10. Okay. If I make it +10, what happened? Okay. Now the power will flow reverse. The power will flow from source number 2 to source number 1 by just changing the angle. Okay, direction. See, 10 degrees. Okay, and you can see the power difference. It just change the flow. The power is the same. You can change the flow. Okay, look at it. Okay, so again, if we increase the wattage here, you see you can even control. I want the real power to flow in this direction, but reactive power to flow in this direction. Also can. Okay, so in some condition we need to do that on the. So in other words, is real power and reactive power not necessary to be flow in the same direction. They can be opposite. to each direction. Okay, or in this case, okay, I reduce the source 1 voltage to 270, and you can see that I can control, both real and reactive power, okay, from source 1 to source 2. So you can actually play around with the software, okay. I put up here so you can have more, what we call this, can experience, the changes of all this. Okay, let me see. Where is my program? Oh, how come we come here? Power line, I think it's under power line, I'm not sure. Oh, power flow, okay. Okay, you can. Okay, power flow. Yeah, you can actually play around, like I said, okay, you just put in negative to positive, okay. Yeah, the arrow will change, okay. The arrow will change, you put back negative here, okay, then yeah, direction change, you increase the voltage, okay. You can see that, it should show the direction, okay. This one, I believe you all study the energy conversion transmission line, right? You study the, I'm not sure, maybe you just focus on the cable, okay? Nothing wrong, but this is to let you know that with the help of power electronics converter, right, you can actually control. But in the old days, totally not controllable one. It depend on your load. The higher power of your load, right, it would just drag more power, right? So that means it will sometimes cause the grid to be uncontrollable. But now with this, what we call this FACT system, you can actually control how much power you want to send to this substation. So it's no longer depend on the load. So if it's depend on the load, right, what happens if the power exceeded the cable limit? The cable will actually burn up, or snap. All right. So now with this FACT system, you can actually control it. Okay, you can actually control it. Okay. All right. So in order to do control, okay, of this, active reactive power thing, okay, like I say, the most fundamental one is the static, okay, VAR compensator, SVC in short. Okay, so in SVC there are basically two types. Okay, it's a TCR, okay, and a TSC. So the difference between TCR and TSC is TCR, you can see that again, you will see these two thyristor, okay, in opposite. This is the AC controller, and it is connected to a reactor. Okay, so you can identify them by the last name reactor. Okay, last name capacitor. Okay, so the difference is one is capacitor, one is reactor. So reactor absorb the what we call this reactive power. So it changes the direction of the reactive power. Okay, so for capacitor, it's inject, okay, the reactive power to the grid, so it will cause the change of direction of the reactive power. Depend on, if you turn it off, then nothing happen, right? It will just flow according to the load. So if you want to say, oh, I want to change the direction of the flow, okay, then you switch them accordingly. Okay, this is just a transformer, okay, because you don't control this one directly to a 275 kV, right? So you usually have a transformer to step down the voltage. So that is much more easy to control, okay? Okay, so if we look at one of the example, yeah, this one I think I haven't downloaded, but anyway, just for demo purposes, I start with TSC. Okay, TSC, okay, we have a AC, okay, and we have a capacitor. Okay, we have a capacitor here, and we have a thyristor, okay, in both direction. Okay, and then we measure the current, and we measure the voltage. Okay, we measure the current, we measure the voltage from here, and of course, what we need to see is that we will need to see the active power and reactive power. Plus negative is the direction. Okay, it's the direction. So this is a simple circuit without any load, just to demonstrate. Okay, if we, what we call this, turn this on, what will happen? Okay, to the power flow on the line on top here. The load here, okay, basically when I open up, okay, I will set it to the reactive power of the capacitor is just 100 for the sake of demo, because in real life we don't do this control at 220 volt. That's LV. It's all kilowatt, okay, 100 and above, okay, but this just to demonstrate, okay, some of the setting, okay, the source setting, and of course the the firing angle, okay, it's the same as what we already learned. Okay, and this is what happened. Okay, when we turn off, right, there is no current flow. Okay, there's no current flow. This is the voltage. Okay, and there's zero current. So when we turn it on, what happens is that you will start to see that we will have the current. Okay, the top one is the current, the bottom one is the voltage. And you see the current and what we call this and the voltage, right, out of phase 90 degree, right, and it's a capacitive, right, so it is leading, not lagging. Okay, so it's leading, so you will say that, oh, okay, so we will have the negative reactive power. Okay, capacitor is usually used to compensate the power factor or the reactive power . Okay, if we, let's see, okay, all right, so okay, for this one I already run. Okay, again it will have 100, right, because we set 100. Okay, yeah, we will set them, okay, almost 100% on. But of course, when you change a bit of this firing angle, okay, so maybe we're firing a little bit different, not half anymore. Okay, 1/3. See, now different is that reactive power reduced from 100 to 62. Okay, and now I got active power going in already. Okay, I got active power. Okay, that is what happened. Okay, to the current waveform. We cut it a different way, so you will see that, okay, we control, okay, this power. But in practice, for TSC, okay, this one, switch capacitor. You see the word switch. Okay, the word switch means that they don't actually cut them at a different firing angle. They either turn it on or off. Okay, they don't really like what I'm trying to do, because it will distort the current. Okay, so they don't actually do that. Okay, so that's why it's called switch. So if you want to have a different power, right, what you will do is that you just have to change the, what we call this, the capacitor . Okay, in the actual system, you will see there are many of the capacitor there. So it depends on how much power you want. Okay, you will switch to that particular capacitor. It operates just like a cap bank. Okay, but it's electronically controlled. Okay, let's come back here. Okay, now. Okay, we run this again. Now it's turned normal, right? So usually you can see the real power is almost 0. Okay, then of course, if you change this to 200, and you get 200. You want 300, you get 300. Okay, so usually when the engineer design SVC, right? SVC is only operate on a certain line only, right? So they will roughly know how much reactive and active power you require to compensate for that line. So they will have a set of like 10 or 20 capacitors with different range. Let's say each of them is 100. They got 10. You can control 100, 200, 300, 400 up to 1000. Okay, for example. All right. So by doing that, right, you are actually changing. You are causing this what we call this the phase angle different. Okay, the phase angle different between the two sides. Okay, the phase angle different between the two sides so that you actually control the reactive power. Okay, so let me stress again, for TSC, they don't really control maybe half a bit. You can do that, but in practice they don't do that. Okay, they either turn it fully on or fully off. That's why they call it switch capacitor, either switch on or off. Okay, they don't do it halfway, a bit different angle. They don't do that. Okay, but practically you can do that if you want, but they don't really practice this in the grid industry because at the transmission line, the harmonic, they have to make sure that the power is clean. As the voltage go higher, right, than 275, 500 kV, right, what we call the quality of the power, okay, has to be the most pure, all right, the most clean types of power quality lah. Okay. Okay, I think we have to stop here, almost 9:30 already. All right. So yeah, 90 degree because we switch at 90 degree. That's what happened. And okay, TCR, we will talk it in the next class. Okay, we should be able to end this in the next class already lah. Okay. So okay. So up to this point, any questions?
No questions.
Okay. All right. So yeah, I think if no questions, okay, we can end our class today.